Thank you very much, Sebastian, for this very kind introduction, and thanks a lot for inviting me here to come to Toronto and to give this talk at the Fields Institute. It's a great pleasure to be here. And as you already said, I will speak about joint calibration of SPX and VIX options with signature-based models. And this is joint work with Guido Gazzani, Janka Möller, who are both my PhD students, and Sara Svaluto-Ferro, who is in Verona. So here's an outline of my talk. So I will start with a brief introduction, then give you an overview of signatures of continuous semi-martingales. Then I will talk about VIX options and how to price them with these signature-based models, and then also on SPX options. And finally, I will address the problem of joint calibration of both SPX and VIX options.
Big fat button. Oh,
yeah.
Okay. You know what? I might have ruined it by clicking on a Zoom thing. Let's see. And try now. There
yes, very good. So what are signature-based models? So as you all know, now we often deal with machine learning approaches, and this also means that highly parametric and over-parameterized models gain in importance also in finance. And the goal is now to learn not just a few parameters as in classical models, but just the whole model as itself or the characteristics of its model. And it depends on what kind of a universal approximation theorem one relies. This yields different classes of model. And what we consider here are so-called signature-based models. And this means, and I will explain what signature is exactly, that the model itself or its characteristics are parameterized as linear functions of the signature of some underlying process. And in the simplest case, this underlying process could be Brownian motion, and then one considers the signature of this Brownian motion and the linear function of it for the characteristics or the model itself. And this is inspired by several papers. The first one is by Imanol Perez-Arribas, Christopher Salvi, and Lukas Spruch on so-called SIG SDEs for quantitative finance. Then a lot of work by Terry Lyons, who is the father of rough paths, and this is very much related with signatures. So this is the paper by Terry Lyons, Sina Nejad, and also Imanol Perez-Arribas on non-parametric pricing and hedging. And we have another paper together with Guido and Sara on signature-based models, but there we only considered pricing and calibration to SPX options. And signature methods become very popular in mathematical finance recently, and here is a list of papers who contributed to this literature, and it's certainly not exhaustive because it's growing a lot, and I'm sorry if I forgot somebody. Okay, so what is the goal in this current work of us is to calibrate jointly to options which are written on SPX and VIX accurately and in a numerically efficient way. And this joint calibration is still regarded a little bit as the holy grail of volatility modeling, even though recently significant progress has been made by several different approaches, and I will give you an exhaustive list when I come later to the joint calibration problem. In a nutshell, what is the challenge is to reconcile on the one hand the large negative skew of SPX options implied volatilities, and on the other hand the lower implied volatilities that arise from VIX. So this is somehow a problem, and classical models do not really manage to do that. So what is the modeling framework that we consider here? We consider on the one hand side actually as classical stochastic volatility model, where we have these dynamics for the price process. So this would be our asset price process. So this is a classical diffusion model driven by some Brownian motion. So this is for the discounted dynamics here. And the volatility process that enters here, so this is the sigma S, this is non-classical in the sense that this is a linear function of the signature, of the time-extended signature of some d-dimensional semi-martingale X. So we have a d-dimensional semi-martingale X. This bold thing here with the head denotes the time-extended signature of this X, which I will define on the next slide, but just that you already know what is the modeling framework. And this scalar product style brackets here, they are just a linear function of this signature process. And in fact, so this semi-martingale, what we call primary underlying process, this is a fixed semi-martingale exogenously given or somehow estimated, where the dynamics come with certain parameters which are not trained. So this we consider in the language of machine learning as hyperparameters. And what we actually train are these parameters L, so the parameters of this linear function. So this has been found by calibrating to options on SPX and VIX. Okay. So let me give you already the implications of this modeling framework. So it can be seen as universal in the class of continuous non-rough stochastic volatility models because this is of this universal approximation property of the signature, which I will show you on the next slide or in the few slides ahead. And on the other hand, it's not only approximative, but it nests also some classical models and also a recent one by Eduardo Abicaba and co-authors, the so-called quintic Ornstein-Unbeck volatility model that jointly calibrates SPX and VIX. So this is their recent paper, and there they show that this calibrates very well to a time series of SPX and VIX options. And this is actually nested in our framework. Another feature is that if we have, so our primary underlying process is this X, so we add time, this I already said, and we also add the Brownian motion which drives the process. And then I call this process Z. And now not only the volatility is a linear function of the signature of X, but also the log price can be expressed as a linear function now of this further extended process of the signature of this Z hat. And this gives further tractability properties. In particular, if we choose our process X to be a polynomial process, I will introduce that as well, then we can compute the VIX analytically via a matrix exponential. So this is the nice analytic tractability of this framework. And this in turn allows to use a Monte Carlo approach for option pricing, which is actually really tractable, since we can always compute offline the signature samples of this Z hat. So this we can use once for all for the whole optimization and calibration task. So we have an offline sampling and then a standard optimization. And therefore, you can really use Monte Carlo in a calibration task. And what we then show also, or what comes out, is that one can actually solve this joint calibration problem without jumps and also without rough volatility. This has also been observed by papers by Julien Guyon and also by Eduardo Abicaba. So this is in a nutshell the outcome. And now let me start by introducing rigorously the framework that we have. So what is signature? So signature goes back to Chen already in the 50s, and it plays a major role in rough path theory, which was initiated by Terry Lyons, and there are many books on that. So for instance, by Peter Fritz and Nicolas Victoire, also Peter Fritz and Martin Heyrer. And here I consider it for a d-dimensional semi-martingale X, and there the signature is defined as follows. So this is a sequence of iterated integrals where we start with 1 here, And then we have the first integral. So this circle here is the Stratonovich integral here. And so this first thing just means that we have a vector which just gives the value xt minus x0. And then we have the second iterated integral where each of the components is integrated with each other. And here you have to bear in mind that this is not commutative because it matters how you integrate. And so here you get the D times D matrix. So this is here with this tensor product. And then you continue and you have all these higher order iterations. So here I spelled it out for the case when D is equal to 2. So we start with 1, then we have this vector, this two-dimensional vector, then we have this matrix here, and then you can consider the higher order tensors, and this is then the signature, and the notation for it is again with this bold symbol. And whenever time is included as a component of the process, then I write it with the x hat. And when we truncate at level n, then we have here this n. Okay, so this signature, as you saw it, is sequence valued. It takes actually values in this so-called extended tensor algebra. So what is this? So we can consider this n-fold tensor products of Rd. This is that. And then we can define the extended tensor algebra of Rd as such sequences where every element in this sequence is an element in this n-fold tensor product of Rd. And for further use, I need also a basis of this n-fold tensor product of Rd. So I have a multi-index I consisting of indices which takes values from 1 to in 1 up to D. And then the EI is this tensor product of this canonical basis elements of Rd actually. So this would be the basis elements here, and this is then used to extract an element of this tensor algebra. And when we truncate at level n, then this is denoted with this Tn here. And of course, we can somehow flatten this tensor algebra. It has actually, so this, when we truncate at level n, then the dimension of this is given by this expression here. And so we can, so this is then isomorphic to this Rdn. And then we often have some labeling function which makes a vector out of these elements in the tensor algebra. And what we also write here, so this ui here is when we extract the e, so the ei component of an element here. Okay. Good. And now coming to linear functions of the signature. So we write this with this scalar product here. So this just means that we take the EI component of the signature and multiply it with an index Li here and sum this up. So this is a linear function of the signature. And why are these linear functions of the signature? Why are they nice? Well, now comes this universal approximation property that I already announced. So in fact, we have two crucial properties which allow us to apply the Stone-Weierstrass theorem. The first one is the point separation, which means that if I take the signature of a time-extended process xt, then the signature at the final time, capital T, determines the whole path from 0 to t. So this is this point separation. The second one is the algebra property that if I have two linear functions of the signature, then the product of these two linear functions is again a linear function, and I can express it with this shuffle product here between these basis elements here, and this gives me a new linear function. So polynomials on the signature reduce to linear functions. So this is not true on the whole tensor algebra, but only on the signature, of course. And then I can apply the Stone-Weierstrass theorem, which tells me that I can approximate continuous path functionals. So here functions up to the second level of the signature actually. So one has to have this continue up to the second level. With respect to a certain p-variation norm, I can approximate it uniformly on compact sets of paths with linear functions of the signature. So this is the essence of this Stone-Weierstrass theorem. And what does it mean for? I'm sorry, what did I do now? I put it too long, maybe.
It could, yeah, it could be default too long.
Yeah.
Okay.
Thank you. For our purposes, it means that I parameterize my volatility as such a linear function of some underlying process, a linear function of the signature of some underlying process. So this means that any path functional of this x, so if it's a very general framework, can be approximated via this linear function.
Christa,
okay. Yes?
can I ask a question? So in the previous slide, in the previous slide, you choose the functionals of the second level of the signature. This is just by choice. It could be any level, and the theorem would still work.
It's just could be, of course, only the first level as well. Yes.
Thank you.
Is only that meaning that we have continuous functions up to the second level, so that the continuity applies to that for this reason. You're very welcome. So now let me come to VIX options with signature-based models. So what is the VIX? First of all, this is a measure on the market's expected volatility of the S&P 500. So I use SPX and S&P 500 interchangeably. So the one is the SPX is the symbol actually of the S&P 500, and the options are written on SPX actually. And in fact, what is the definition? So the current VIX index quotes the expected annualized change in the SPX 500 over the following 30 days. So in formulas, it's given by this expression here. So you take the increment of the logarithm of the asset price in 30, so capital T plus delta. So delta is 30 days. So this is this increment, and then you compute the conditional expectation conditioned on FT here, and then you take the square root of this. So this is the definition of the VIX. And we now consider the specific model framework that I already showed you at the beginning. So we have this risk neutral dynamics for the discounted S&P 500, where the volatility is actually a linear function of the signature that I will introduce on the so that the dynamics of or the underlying process that we consider is on the next slide. So the B is a Brownian motion. This will be specified with a linear function of the signature of an underlying process. And for notation, the V is the sigma square, so the instantaneous variance, and we suppose that this is finite. And under this condition, on this modeling condition, one can write the VIX. This is well known in the following formula. So the VIX is then actually the square root of this 1 over delta times the expected value of the integral of the instantaneous future variance conditions on FT. So this is the integrated forward variance actually. So this is standard in such a diffusion model, just by Ito's formula. And now, as I already said, so the assumptions on our volatility is now that this is a linear function of the time extended signature of some d-dimensional continuous semi-martingale, and we suppose that this x with b has a certain correlation structure. So the Z is xp, so this is the notation for the underlying process together with the Brownian motion driving the asset price, and we have a certain correlation structure. This is given by this row here, and the parameters of interest are these L's here, that appear here, and this is what we would like to calibrate. And the semi-martingale that we consider as primary underlying process, this is something fixed. Okay, as I already said, it can in principle approximate any stochastic volatility model, which is, let's say, non-rough. And but some models are also nested there. So for instance, if X is a one-dimensional OU process, and then you consider these parameters like that, then you recover the Stein model, for instance. You can also recover the Saber model when you have the beta equal to 1 in the language of the Saber model. Then you, as I already said, you know what. This is when I do 2 times. That's
Yeah, I guess it's a default for some reason.
maybe.
I don't know how to change that default.
Maybe if I do it here. Yeah, is it better here? Or?
It's been working fine.
Yeah, I don't know. Sorry. Yes. So also the model by Eduardo and co-authors can be recovered. In fact, when one takes the signature up to level n equal 5, then one recovers this. So in fact, of course, we have to truncate our signature for the specification of our linear function, and we have to do it at a certain level. And here you have to go up to level 5 in order to recover the model of Eduardo. And just to say, I mean, now on the previous slides, maybe to go back. So this is our specification here. So we consider the signature starting from some initial time 0, and we consider this then always from that time on. One could also say, I do not want to have one fixed starting date in time, but I just want to go back. This is, yeah. I only want to go back in time. What I consider from my underlying primary process is just the lag delta. This one can also consider, the formulas get a little bit more complicated, but this would be a different and maybe more, sometimes more economically reasonable assumption for the volatility process. But one can still get similar tractability, which I will now show you. So in fact, what we will do for our implementation is to consider a specific semi-martingale, namely a d-dimensional polynomial diffusion process. What is that? This is very simple. This is a diffusion of that type where the drift is an affine function in X, and where the A of xt, so this diffusion matrix, is a quadratic function in X, in the state. And W is a Brownian motion. And under this assumption, this is the very nice feature of, one of the nice features of polynomial processes, is that the truncated signature is then also a polynomial diffusion itself. And when it gets this kind of formula, so it means you have here an operator, and this operator here, this maps the truncated tensor algebra is mapped again into the truncated tensor algebra, and this means that I can compute the expected signature of this truncated, so the expected truncated signature with a finite dimensional matrix exponential, because it solves a linear ODE. And this is nice, and that's what we use. So there are many, for people who do not know what a polynomial process is, but this is the definition. So you can see that this nests a lot of models, in particular geometric Brownian motion, Ornstein-Uhlenbeck processes, Cox-Ingersoll-Ross processes, Jacobi processes, and so on. So this is a very rich class. And it now has the following implication for an expression of the VIX. In fact, we get this formula for the VIX. So I took the formula from before with this integrated forward variance. And in fact, so what appears here are our parameters L, that parameterize my linear function for the volatility process. And then I have this Q here, and this Q function is given by this expression here, where now this matrix exponential appears. And here these are some coefficients, and this is the vectorization of the signature at time capital T. So this is the expression for the VIX. And now you see you have the L's here, and you have this Q, and this Q only involves the random terms that I have to sample, and the optimization then will be only done over the L's. And this is this nice split between you can sample in advance and optimize then only over the L's. And yeah, and here's this matrix exponential with this G function that is associated with the generator of my polynomial process. And this Q is positive semi-definite, therefore you have a Cholesky decomposition, and you can also write it with this formula here. Okay, so now pricing of VIX options. So VIX options are actually written on future contracts. So the price of a future at time t is simply the conditional expectation given here. And if you calibrate to VIX options, you also have to calibrate to the futures in order to get the right model implied volatilities. So you have to not only calibrate to the options, but also to the futures on the market. So what we then do is on the one hand, when we calibrate to call options, this is then our model price. So we calculate the VIX like I showed you on the slide before, and then so we do Monte Carlo, as I said, because it's tractable in our case, because we can sample everything that is related to this Q that you saw before, the U, so the Cholesky decomposition, and then the L's appear, and this is simply the payoff and then the Monte Carlo price in our model, and this would be the price of the future contract. And you see, for every L, we can use the same samples, and this means we have no simulation during the optimization task, and one can additionally, if you want, you can apply some variance reduction techniques here that you add to this model price. Okay, now what is the calibration functional that we consider? So we go over maturities and over strikes, and this is a loss function where comes in the model price, the market, the model future price, the model option prices, and then the market prices with bid and ask, and also the corresponding implied vol and the market future prices. And we choose a particular function for this L here. So in fact, we want to calibrate to the future prices and also to the option prices. So here we have the mid price from bid and ask from the market for the options. Here comes the difference between the market prices for the futures. So actually this one here and the model one, and we weight this with the market delta. And here we have some, so we have this beta here can be either 1 or 0. So if it is 0, then here we just take the model price. If it is 1, then this vanishes, and then we only care about if we are in the bid-ask spread or not. And here we have a so-called Vega weighting here. So these are the Vegas, and in fact, this choice of the loss function comes from a Taylor expansion of the Black-Scholes price in terms of the Vega and the delta. So this is the reason behind this. Yes, of course.
Just to make sure that I have the model straight in my head.
Yes.
So one of the inputs were the parameters for the underlying city market. And if you know those parameters, then you can calculate the signature, and then you can try to find the linear function.
Yes.
what assumptions are you making about the underlying?
I will show you in our calibration, but it's a very good question. So in fact, we will take a two-dimensional Ornstein-Uhlenbeck process with certain parameter choices, which we know from other models that were calibrated are quite good. And then we just calibrate the Ls.
Are you calibrating the semi-martingale parameters?
No, not at all. So these are these hyperparameters. One could then do some hyperparameter search if you want. So, but in our procedure, we just fix them, and then we can just calibrate the Ls. Yeah, I think you have the model straight in your head. Yes, these are already. What did I do now? I went in the wrong direction. So this is, yes. So now here are the first numerical results. Actually, with a two-dimensional OU process, we go with the signature up to order n, and here are these, what I call hyperparameters. So these parameters are fixed, the kappa, the theta, and the sigma of the OU process, and then also the correlation matrix here between the OU process and also with the Brownian motion that is driving the price process. But this does, I mean, this is not relevant in this case because it's only, here's only the single optimization task on VIX. And so we consider here these 6 maturities. So we start with 14 days, and I think, yeah, something like 4 to 5 months, yeah, something like that. And yeah, you see that this is quite accurate. So we are always in the bid-ask spread systematically with this model. And also here, so we calibrate it also to the futures. So here you see the futures term structure, and again the calibrated prices and the market prices, and this is also very accurate. So this is, but this is, I mean, just a single, not the joint calibration task. Now let me come to SPX options. So here the goal is also to have again this procedure where we can sample offline and only optimize the Ls afterwards. And in our previous work, we were considering a linear model of that form for the asset price. So now we are not exactly in that framework because it will turn out that the log price is similar to that. And in fact, so the goal is we have now this model here, and we would like to find an expression for the price process in terms of the signature of this extended process. So we have our x hat, so time and x, the underlying semi-martingale, and the Brownian motion here. And we now would like to express this in terms of the signature of this z hat. And this is subject of the further proposition. So now what we suppose, and this is always satisfied in our polynomial framework, is that the quadratic variation is again a linear function of the signature of the process itself. So this is in many models satisfied, in particular in the polynomial ones, because in this case you can write the integral with respect to ds of that again as a linear function of the signature. And also if you consider the E2 integral here, then you can also write it as a linear function of the signature, where this E tilde here have a certain expression here coming with this quadratic variation. And so now this is the expression for the price process in terms of the signature of this Z. So again, the Z is this combination of X and the driving Brownian motion, and we can write the price process like this. So we have with an exponential, then we have again some Q0 matrix with these parameters L, and here something linear in the signature. And yeah, here I do not want to go in all the details. This Q0 can be computed like that. So you see that this depends again on the signature of X, and the L's enter here quadratically and here linearly. And this in particular means that you can express the log price as a linear function of some u depending on this L of the signature of this Z hat. And this has other implications because this Z hat is now also a tensor algebra valued affine process. This is because everything linearizes in the tensor algebra, and therefore you can also compute the Fourier Laplace transform of this Z analytically, of the signature of this Z hat, via solving an infinite or a tensor algebra valued Riccati equation, and then you can apply. Yeah.
That's true regardless of what the semi-martingales are.
So it's in particular for this polynomial, but also for more general ones. So if you write down a so-called signature SDE, where you have that your coefficients in the SDE, so just think of a normal SDE with drift and volatility, and then you say that your drift is a linear function of the signature and also your diffusion, then the signature of such a thing is again an FM process. So this is so there you can really have path-dependent characteristics in form of this linear thing, which can not only linear functions that you could truncate at some level, but it can also go to the limit so that you really have in the one-dimensional setting analytic functions there. So that's really nice actually. And yeah, when you can compute the Fourier Laplace transform, you can also use Fourier pricing. And so we did not exploit it so far, but I think this is another, yeah. So now let me come to the joint calibration. Here is a list of, certainly non-exhaustive, of contributions to the literature on this joint calibration. So everything started with a double CEV model by Gettrell in 2008. Then there was some literature where jumps were included. Then there's there are many optimal transport approaches also to that. So here I mentioned these papers by Gu, Guyon, and so on. Then many rough volatility models have been calibrated to that, so by Gettrell, Mathieu Rosenbaum, Römer, Jacquier, Abitschaba, Bondi. Then many machine learning approaches were used to calibrate also these models and also neural SDE models. And so recently this Gaussian polynomial volatility models by Abitschaba, then multi-factor rough models by Römer, path-dependent models in a somewhat different sense by Guyon. So yeah, again, I'm sorry if I forgot somebody, and yeah, if somebody in the room has contributed, I'm even more sorry. So yeah, so now we calibrate to both. So this means we have again some calibration functional, and now we have to make a convex combination of calibrating to SPX and calibrating to VIX. So here is again this SPX, which is very similar to before, and now we make this convex combination, and we can as well introduce variance reduction. And again, so here are the maturity and moneyness specifications. We have now a three-dimensional OU process with these kind of hyperparameters. So they are again fixed and not calibrated. And here are the results. Again, so here we have this different, we have 5 different options, or not options, but maturities that we consider. So for 3 for the SPX and 2 for the VIX, and you see from these plots that we are always very accurate and always within the bit aspect, and everywhere where you have this line, this corresponds to the future price in the VIX options to which we calibrate as well. So this is the second and the fifth plot here, where this is the VIX options, and here you see exactly the different smiles or the different behavior of the implied wall. So the standard smile thing for the SPX, and then this concave function for the smile. So it's not really a smile. Yeah. Yes. And this is also, so this is now showing you how does the time series look. So we only calibrated here 2 options, but the nice thing is that if you sample now from your model with the parameters L that are calibrated to the options, then also the time series looks quite nice. So in fact, what you see on the first plot, this is a trajectory of, so the red one is the VIX and the blue one is the SPX. And you have really this negative correlation that you can see here. And the second plot, this is just the, so it's very similar to the VIX because it is the instantaneous variance. And yeah, yes?
So I'm sorry for getting confused.
No, please.
So you're doing some kind of machine learning to do the calibration to find the linear function.
So in order to find this L, so this is a standard optimization actually that we do. So we compute everything before, so we compute our model prices. The L's, this is what we have to find, and we do a standard optimization to find these L's. I mean, it is even standard optimization, some gradient descent, yes.
But what are you calibrating? You're looking at a time series.
No. We look, so we have option data. So maybe I go back. So these, sorry? Yes, so on different maturities. So these are options in the future. The price is quoted today. So this is an option that expires, let's say, in 14 days for the first option. The price is quoted today. I now have for these different strikes, let's say in order to do the first one here, this one, I have today my prices on the market for my option on VIX that expires in 14 days. And now I have my model, I compute with my model the prices of that for different L's. And I look now for the L which matches my prices best.
But you don't need to observe the value. The semi-martingale isn't observed.
No, I just took this is really something underlying which I mean, you could think of something econometrically reasonable, what should be somehow a driver. This we did in our other work somehow, but now this is really some exogenously given something. You could give a meaning to it, but here we do not really do that. You're very welcome. Yes, and then this is, so when we now sample from our model with this given semi-martingale, we get this kind of trajectories which reflect also a good time series behavior, what we would like to have. And now, I will finish very soon. We also extended this with time-dependent parameters so that the parameters L can depend on the maturities, then we get similar tractable formulas, and we get somehow a rolling procedure to calibrate, and then we can go even further to further maturities, and the calibration results are equally good. And it's I mean, to go very far, one needs this time dependence. And so here again you see calibration to VIX and to SPX, and both are really accurate. And so to wrap it up, so it is a universal modeling framework in the sense that every continuous non-rough stochastic volatility model can be approximated. It nests also a lot of models, and both the volatility, so by assumption, but then also by calculation, the log price can be expressed as linear functions of the signature of this underlying process set, containing also the Brownian motion. Within the polynomial specification, we get really nice formulas, and therefore a Monte Carlo approach works. We can calibrate separately. And for several short maturities, the joint calibration problem can be solved without time-dependent parameters. And finally, when we go longer. We can use time varying things. And so thank you very much for your attention. Here's just a list of references.